The next unit is a bit of a digression on what's known as Russell's paradox. Wait for it. Not what you were expecting. What is this? So this is an excerpt from a mathematical comic known as Logic Comics. It was written together by a group of people, including a couple famous computer scientists. So anyway, this fellow is Bertrand Russell. I'm here to speak about my affair with logic. So I'll stick to that as much as life will let me. Okay, now, scene with the rain and the umbrellas, okay? Sets, you say? I thought you were interested in numbers. I am, but sets are at the basis of number. Oh, what is 3 but the set of all sets with 3 elements? Threeness is the common property of 3 umbrellas, 3 horses, 3 hats, 3 cookies. Sets have most interesting properties. Really? And I thought them boring. Fool. For example, a set can contain other sets, or even itself. How can a set contain itself? Well, the set of all ideas is an idea. Therefore, it contains itself as an element. But not all sets contain themselves. Oh, no. No. The set of birds, for instance, is not a bird. I say, that's an interesting dichotomy. The set of sets which contain themselves, and the set of sets which don't. About which, well, we can ask, does it... Wait a minute! So what is this predicament that Bertrand Russell found himself in? Comes again to this question of what about the set of all sets that do not have themselves as an element? Okay, so this is the set W here, using set builder notation. Say we have the set, all of the S in sets, these are the elements of W, such that S is not an element of S. Okay, that is, a set is in W if and only if it's not an element of itself. Okay, interesting. So then the question is W an element of W? Okay, so here, how would we determine this? Is it the case that W is some example of an S? Okay, such that, so it's such an S is in W if and only if it's not in itself. That is, we get W is an element of W if and only if it's not an element of W. Okay, and this is a paradox. This is precisely this logical conundrum. You're sort of stuck. What do you have? Can this be a set? Can it not be a set? What does it even mean, really? Okay, so this is exactly what's known as Russell's paradox, and this dates back to early 1901. And this is more than just kind of a silly trick or something. This is actually a real problem that kind of questions some of the fundamentals of mathematics. How can you have a logical system that has such a contradiction, a paradox like this? And we kind of find ourselves trapped in a sense. So what is the way out here? Well, there's a couple different options. In some sense, the primary option that's taken is to not allow W, okay, what we've tried to define on the previous slide, to be a set. Okay, and how is this really done? Well, if you see the fine print here, so what is ZFC? You'll see all about that next semester. These are the Zermelo-Fraenkel and axiom of choice. These is a list of axioms that allow us to build rigorously mathematics from the core and build up. Okay? And so don't worry about that for now. Just think of it as kind of the start, and that there are some axioms that allow us to effectively, when we define what is a set, there's some sort of rules that must be satisfied that in particular does not allow a set to be an element of itself. Okay, and this removes the paradox from before. Okay, so if you can't let S be equal to W, then you're saved from the paradox, okay? But then, of course, there's a bit of a downside, which is that when we talk about what is a set, I said something about it's a collection of elements. Okay, but if you need to save yourself from the previous paradox, it can't be the case that all collections of elements is a set. Okay, so this I'm going to leave is some sort of partial mystery. Don't worry, okay, you can sleep tonight. There is a way of continuing, and there is a rigorous fundamentals of mathematics that are built up and that we will be using. But we'll talk a little bit more about this next semester. Okay, and this concludes the end of this unit.